Going beyond just the color, we can go to the intensity of a black body. So think back to that picture we saw before. Remember, intensity is how much light is coming out per unit area. And all of these objects have the same area. The most intense light is the one that's brightest, which again is the yellow U, the hottest of these glowing objects. So intensity of a black body also depends on its temperature. The higher the temperature, the more intense the light. And in fact, this is a really strong relationship. The intensity of an object goes as the fourth power of the temperature. I means intensity, T means temperature, and that funny little sign means is proportional to, which means there are some other numbers that we're skipping, but they don't matter. It just means that the intensity goes the temperature to the fourth power. So if we were to double the temperature, the intensity of the object would go up by 2 times 2 times 2 times 2, which is 16. So doubling the temperature increases the intensity by a factor of 16, which is a tremendous amount. We can see this most clearly in sunspots. So the sun is mostly yellow, and in this picture of the sun from 2000, you can see that most of the sun here is yellow. However, in the sunspot itself, this is a region where magnetic fields have caused the gas to cool off. And so while most of the sun is 5,800 Kelvin, the sunspot is cooler, 4,000 Kelvin. Now that's still ridiculously hot, but if you notice, this part of the sun, first of all, it's a different color. It's orangish red in color. And second, it's a lot less intense light. It's a lot darker in the middle of a sunspot than it is in the rest of the sun. Now, if we were to pull the sunspot off of the sun and hold it up in space next to the sun, we would see that this is still glowing, but next to the very bright, intense surface of the sun, this area looks very dark. Here's another object that has several different temperatures involved with it. This is some wrought iron being worked by a blacksmith. So he put this iron rod in the fire, heated it up, and is now forging it into the proper shape. And what you can see here is that this iron rod has several different temperatures. That it's hottest there at the bottom where it's glowing white, and then it's cooler where it's yellow, cooler yet where it's orange and red, and coolest where we don't see any optical light coming out whatsoever. So that's another example of Wien's law, that color tells us the temperature. But we also notice that where the metal is white hot, it's also glowing most intensely. And by the time we get to the orange and red part of the rod, it's not nearly as intense. So what have we learned so far? We've learned that the color of an object depends on its temperature. Hotter objects are shorter wavelength peaks. Cooler objects have longer wavelength peaks. And we have also learned that the intensity of the radiation depends on the temperature. So here are two objects that are the same temperature. We have the sun on the left and an arc welder on the right. How do we know which object is larger? I mean, you know that the sun is bigger than an arc welder, but how do we know that for certain? This is where some of the power of what we've just learned can come in. It's with a fairly complicated law, so hang with me for a little bit, but we'll get through it. It comes from something called the Stephan-Boltzmann law. These are two more European physicists who studied how objects glow due to their temperature. And what the Stephan-Boltzmann law says is that the total energy being put out by a glowing object, the luminosity of a black body, depends on both its temperature and its size. So the hotter an object is, the more energy it emits, but also the larger an object is, the more energy it emits. So here's our mathematical equation. Let's look at the parts of this. L is luminosity, R is radius, T is temperature, and that funny little circle with a tail on it, that's a Greek letter sigma, and here that just indicates a constant of nature. It's a number that never changes. So we don't have to worry too much about the exact value of that number. The things that can change are the luminosity, the radius, and the temperature. So look at the first part of the right-hand side of that equation, 4 pi r squared. If you remember your geometry, that is the surface area of a sphere. So the larger the radius, the larger the area. And in fact, the area goes as the square of the radius. If we double the radius of an object, its area goes up by a factor of 4. If we triple the radius of an object, its area goes up by a factor of 9. So that first part, 4 pi r squared, deals with the area of a black body. And that last part, that t to the 4th power, remember we just saw that that has to deal with intensity. And as I said, don't worry about the sigma, it's just a constant. So this equation is telling us mathematically what I said above. The total energy output of a black body, its luminosity, depends on its size and its temperature. The Stephan-Boltzmann law is a very powerful relationship for astronomers. And the reason is because from Wien's law, we know that given the color of an object, or if we know where its spectrum peaks, we know the temperature of the object. Then with the Stephan-Boltzmann law, we often know the luminosity of a star, how much energy it's putting out, which means that from these two bits of information, once we know the luminosity and the temperature, the only thing left to figure out is the radius. So if we know how bright the star is and how hot it is, we can get its radius. And this is how astronomers first determine how big other stars are. We can't actually measure their radii. We have to use the Stephan-Boltzmann law to do that. So let's summarize what we've learned in this mini lecture. And this is fairly complicated stuff, so we're going to practice with it in the homework, and we'll practice with it some more next week. But these are two crucial bits of information that light from stars can tell us. First of all, Wien's law. Wien's law states that the hotter an object is, the shorter the wavelength at which its spectrum peaks. So the hotter an object is, the bluer the peak of its spectrum, the bluer it will look. And cooler objects will therefore have peaks in their spectrum at longer wavelengths or redder colors. And Wien's law doesn't depend on the size of the object, it only depends on the temperature. The Stephan-Boltzmann law has two parts. One is that if you have objects of the same size, the hotter object will emit more energy than the cooler object. But also, if we have objects of the same temperature, the larger object will emit more energy than a smaller object. And if we combine all this together, we find that if we know the peak wavelength of a star, we know its temperature. And if we know the luminosity of the star, and we'll talk in a few weeks on how we know the luminosities of other stars, we can determine the size or the radius of the star. So this completes Mini Lecture 3. Please go ahead and complete the response to Mini Lecture 3.